Welcome to this explainer. Today, we're going to completely shatter a fundamental assumption you probably didn't even know you had. You see, when we picture the microchips powering our phones and our servers, we usually imagine this pristine digital world, right? A world where a wire instantly connects point A to point B. But as we're about to explore, that perfect instantaneous connection, it's a complete illusion. Think about the billions of microscopic connections inside the device you're using to listen to this right now. Do they truly transmit data instantly? Do they somehow allow electrical current to flow without any resistance whatsoever? It is so incredibly easy to look at a simple digital schematic, driver, interconnect, receiver, and just assume that the interconnect sitting in the middle is some magical, zero-resistance highway. But the source material we're looking at today hits the nail on the head with this quote. In an ideal circuit, a wire may look like a connection. In a real chip, a wire is a physical structure with resistance and capacitance. That is the core truth here. Every single interconnect inside a microchip actually behaves like a complex electrical network, and it's that physical network that dictates exactly how quickly and honestly how cleanly a signal actually reaches its destination. So here is our roadmap for the explainer. We'll start with the perfect wire illusion, look at a really helpful microchip plumbing analogy, dive into speed and slew, and then we'll really focus heavily on specific VLSI techniques engineers use to fix these flow issues. After that, we'll tackle signal integrity, and finally, wrap things up with extraction and timing.
All right, let's jump right into part one, the perfect wire illusion.
The brutal physical reality of a metal wire on a silicon chip is that it is absolutely not a zero-resistance path. If we look at the basic equation for resistance, resistivity times length divided by cross-sectional area, it tells us a really clear story. Longer wires inherently resist the flow of electricity more, and narrower wires, they spike the resistance even further. In modern chip design, this is a massive headache. Why? Because we are packing billions of transistors closer together, which means wires are getting microscopically narrow and surprisingly long. But a wire doesn't just resist flow. It also acts like a microscopic sponge that stores electrical charge. That's capacitance. It exists basically anytime you have conductors separated by an insulator. Inside a microchip, a metal wire has capacitance to the substrate below it, the layers above it, and the wires running right next to it. And since a larger capacitance requires a lot more charge to actually change its voltage, high capacitance means your signal is going to be significantly slower. Which brings us to Section 2, Microchip Plumbing. Let's make this abstract stuff a bit more concrete. To really visualize these invisible forces, let's step away from the microscopic level and think about household plumbing. If a water tank connects to another tank through a super narrow pipe, opening the valve doesn't instantly fill that second tank, right? The pipe resists the water. We can map this directly to VLSI design. Water pressure is our voltage, the water flow is our current. That narrow pipe restricting the flow, that's our wire's resistance. The actual capacity of the tank represents our capacitance. And a tank that fills up really slowly, well, that perfectly represents a slow slew rate, which we'll get into next.
Moving right along to Section 3, Speed and Slew Explained.
Let's apply that plumbing analogy directly to speed. This brings us to a critically important concept called slew. Slew basically describes how quickly a signal changes voltage, so jumping from low to high or high to low. If an interconnect has high resistance and high capacitance, it creates what we call a strong RC effect. As that RC effect goes up, the transition really bogs down. In engineering terms, we say your slew degrades. This is brilliantly illustrated if we go back to containers. Think about filling a small bottle fed by a giant wide pipe. It fills incredibly fast, right? That's low capacitance and low resistance. You get a lightning fast signal. But what if you try to fill a massive industrial bucket through a tiny little cocktail straw? It's going to take painfully long. That perfectly represents high resistance and high capacitance, which leads to a very sluggish, delayed signal transition. Now hold on, we need a strict engineer's disclaimer right here. A lot of beginners fall into the trap of just saying, oh, delay equals RC. As our source material points out, that is a vast oversimplification. RC determines the characteristic speed of the network, but you can't blindly treat it as the exact propagation delay. The true delay depends on the driver, the entire network topology, input and output transitions, and exactly how you're defining the timing. Okay, Section 4, VLSI techniques. This is the really fun stuff. How do engineers actually fix these flow problems in the real world? Let's focus on the specific techniques. First off, before they can fix the wire, they have to model it accurately.
You could use a basic lumped model, which basically pretends the whole wire is just one giant resistor and capacitor. But on a chip, a wire might cross a massive distance, like say 5 millimeters. Now in the microscopic world, 5 millimeters is literally a cross-country highway. The resistance and capacitance are physically spread out along that entire journey. Because of that, physical design engineers have to use a distributed model. They slice the wire up into multiple tiny R and C sections to truly reflect the physical reality of the layout.
And using that distributed model proves that the physical topology is everything. This leads us to something called Elmore delay. When analyzing these distributed networks, the Elmore delay model shows us that resistance hurts you a lot more if it's placed right at the beginning of a long network. It's exactly like having a kink at the very start of a long garden hose versus a kink at the very end. A kink at the beginning chokes the pressure for the entire volume downstream. This proves to designers that where a wire goes and exactly how it branches out matters just as much as its overall length.
So, what is the specific technique when a wire is just too long and the delay is totally unacceptable? Engineers use buffer insertion. Instead of forcing one tiny little driver cell to push a signal down a massive, high-resistance pipeline, they literally chop the line up. They insert buffers, which are essentially microscopic repeater stations to boost the signal along the way. But keep in mind, it's an intense optimization game. Every single repeater station you add consumes extra battery power. It eats up precious physical space on the chip, and it adds its own tiny bit of cell delay.
Now, you might be wondering, well, why not just make the wire wider, like just use a bigger pipe? And yes, increasing the cross-sectional area definitely drops the resistance. But making every wire wider is a physical impossibility. For one, it eats up incredibly valuable routing space, but it also alters the capacitance and fundamentally changes how the wire electrically couples with its neighbors. It even affects the strict manufacturing design rules. So wire widening is a tool they use, absolutely, but it's a brutal, constant balancing act. And that brings us to Section 5, Signal Integrity and Crosstalk. That balancing act we just talked about gets downright terrifying when we move from looking at one single wire to millions of wires packed tightly together. This introduces signal integrity. It basically asks, does a signal survive its journey with its electrical quality intact? Because of all the physical resistance and capacitance we've been discussing, real-world interconnects introduce massive threats like electrical noise, overshoot, undershoot, and severe waveform distortion. Probably the most fascinating threat here is crosstalk. Imagine two microscopic wires running side by side. Because they're separated by an insulator, they literally act like a capacitor. If one wire, which we call the aggressor, suddenly spikes its voltage, that electrical coupling can inject a noise spike right into the neighboring victim wire. This crosstalk is so powerful, it can actually flip a digital 0 to a 1, or completely wreck the delay. This is exactly why engineers obsessively calculate wire spacing and routing direction.
Finally, Section 6, Extraction, Timing, and Reality. Let's look at the actual workflow.
So how do engineers actually catch all these parasitic flow issues before a multi-million-dollar chip is manufactured? Well, it follows a very strict workflow. First, the physical layout provides the exact geometry, where everything lives. But geometry isn't electronics, right? So step 2 is parasitic extraction. This is where highly specialized software translates those physical shapes into actual parasitic resistance and capacitance values. Only when we have that extracted mathematical model can we move to step 3, analyzing the actual timing. This step is called static timing analysis, or STA. STA doesn't just ask how fast the individual transistor fires, it evaluates the whole entire path. As you can see, the total path delay equals the cell delay plus the wire delay. The interconnect itself is a massive, completely non-negotiable component of the total speed. If you fail to model that physical network correctly using the extraction and techniques we discussed, your entire analysis is completely detached from reality. We've really seen today that a microchip is absolutely not a magical realm of instant perfect connections. It's actually a dense, chaotic maze of microscopic RC networks, fighting resistance, capacitance, and crosstalk every single picosecond. So knowing what you now know about the illusion of perfect wires, when you look at the smartphone in your hand, how incredibly mind-blowing is it that billions of these tiny plumbing networks fire perfectly, billions of times a second, just so you can stream a video? It's an absolute engineering marvel, and it's built entirely on mastering the invisible physical reality of the interconnect.